Yep, and I'd just like to introduce myself a little bit further. I'm Drew Carlson. I'll be covering the solar PV and solar thermal components of the webinar today. I've been working in the energy efficiency and renewable energy field for the past 5 years, and I'm an analyst here with GDS Associates.
And good morning. I'm Mark Burgum. I'm a professional engineer here in Wisconsin, and I was the one that got to go to Puerto Rico and Alaska and Hawaii. It's amazing the places that renewable energy has taken my work. So a quick background into where I came from. I was originally doing civil engineering, and I got into renewable energy because just 10 years ago, I tried to get a remote light, one that would be essentially out in the field or out at a livestock waterer, installed with a PV panel and a battery on it. And ultimately, we couldn't do it because of a combination of township rules and technology that didn't exist yet. And at the end, it cost the client I was working for, I think, $13,000 to run the wire that was required to go out to this light, which makes for a pretty expensive light, and set me off on a path to figure out why I wasn't able to do that, what happened, what the technology was, and how it could work better. It's really incredible if you think about it that was just 10 years ago that we couldn't install a single PV panel and a battery to offset $13,000, and now that's maybe that's going to be under a $500 project, and everybody would just nod their head and say, okay, we can do it. Now, getting specifically to renewable energy and agriculture, I guess the best place to start is that agriculture already does renewable energy in lots of places, in greenhouses in the middle, drying grain in the field through the wind and the sun, light coming into barns. We put a lot of clear panels on and things, and then even in the right-hand corner is a irrigation channel gate, which the irrigation system behind it is actually working completely off of the elevation difference in the hydroelectric power. And we'll take a second to celebrate that. In agriculture, these are the things we've done and we do as a normal course of action. And what we're looking to do a little further. Hold on. The slides are not moving. So, one of the things, hold on, I'm having a select. There it is. All right, so these slides are the renewable energy that we are doing as a matter of course in agriculture is a lot of times considered efficiency, because what we're doing is we're taking that solar energy, that wind energy, that elevation difference in the water, and we're using it within its normal natural state. We're not converting it to anything. So a lot of times this is considered as an efficiency project to utilize that information. What we're going to be looking at today is some types of renewable energy that collects that energy, transforms it into something else that creates a more reliable energy source, a more on-demand usage, and a kind of more efficient collection of that resource instead of just what's easily available. All right, Drew, you want to click into?
Yeah, so today I'm going to be, like I mentioned earlier, I'm going to be covering solar PV, also the proper terminology, solar photovoltaic, but we know it as a common name as solar PV, and then following up with solar thermal. I'm not going to be getting into all the nitty-gritty details of the system components and that sort of thing, but what we're really trying to do here today is kind of give you a brief, broad overview of the systems and how they relate with your agribusiness on your farm, and see if we can help you match up the right one for your agribusiness. And so basically, solar PV systems collect photons from the sun and convert them into electrical power. There are multiple different types of systems in solar PV. The most common is the grid-tied system, which is a PV system that is directly tied into the electrical grid. The photo over to the right kind of gives you a brief general description of that, with also has an option on there for a battery as well. This, the system that has been diagrammed here would be known as a hybrid system, where the system is tied directly to the electrical grid, but it also has a battery involved as well. And so that is the hybrid system. There are also battery standalone systems, which are becoming a little bit more prevalent in the industry due to the cost of batteries becoming less and less as technologies develop further. Now, general ideas with the solar PV systems on the price is that it has dropped, like Mark had mentioned, over the past 10 years and really since its inception, but it is still tends to be expensive without having incentives or grants available. So there are kind of four main components of the solar PV system. I'll just briefly cover here. You have modules, which can also be known as solar panels. And this is the point at which the energy from the sun is collected and transferred into a direct current, which then is transferred into an alternating current, which is the most common type of current that we use in our homes and on our farms. And this is done by the inverter, which can be seen in the photo in the top right-hand corner. This is actually a photo from a system that is at my parents' home, and this is a 12.4 kW system that helps power the home for heating and cooling, as well as their electrical needs. And so basically you have the direct current that is created by the PV modules or panels, and then that current is transferred to AC, which is then connected into your home and also connected to the electrical grid at the interconnection point. When you're tied into the electrical system, the electrical companies, electrical utilities need to be able to measure the amount of energy that you're producing and using at the same time. And so this is where you'll have a meter installed, which can be a bidirectional meter like the one pictured in the lower left-hand corner. And it's also, systems are also set up with two separate meters, one that is measuring the energy usage, and then one that is measuring your production from the PV system. The last component of a PV system that I'm going to chat about is the rack component, or the mounting component. The picture in the right lower-hand corner is of a basic ground-mounted rack array. Another option for a ground-mounted system is a pole-mounted PV array, which is similar to the racking system, except for it's usually mounted on a single pole, and there are multiple poles spread out across your coverage area. Another option is directly mounting the solar panels or modules onto the roof of an existing building. So how do you know if solar is a good choice for your agribusiness? Well, I mean, this seems like a kind of a simple answer, but does your agribusiness use electricity? And so lots of our different types of agribusinesses, whether you're a dairy, operation, whether you're a cash crop farmer and use irrigation, or greenhouse production. Lots of these types of businesses use electricity, and if you're using electricity, solar can work for you because solar produces that electricity directly. So when you're looking at whether or not solar PV is a good option for you, some of the different factors that you should take into consideration that are directly at your location is the first thing is the solar resource, which is basically the solar installation, and that's measured as the kilowatt hours per meter squared per day. And basically what this is talking about is I kind of like to think of it as frequency and intensity of solar resource that's available in your area. And so, as you can see, the photo to the right is from the National Renewable Energy Laboratory, which is a basic coverage of the available solar resource for the different parts of the United States. And as you can see, it does vary across the United States. We're up in Wisconsin, so if you look up in Wisconsin, we're in the green, and we have a little bit lower solar resource compared to an area such as, say, Arizona, New Mexico, and Colorado, which has a higher solar resource. And part of the reason for that is our climate, which factors into cloud coverage throughout the year. An example would be Wisconsin, which I believe roughly has 160 sunlight, full sun days, versus somewhere like Colorado, and areas of Colorado which have over 300 days. And so climate plays into it. Then also the seasonal fluctuations. So as many of people who run agribusinesses are aware, the sun moves in the sky throughout the year. And so depending on certain types of year, the solar insolation is higher. An example would be in the summer, it tends to be higher because the sun is moving more directly over us, which is closer and more intense, versus in the wintertime when it's more to the north of us and less indirect and intense. Some other factors that you'll want to look at when you're looking at solar PV is the available space that you have. Whether that's on a clear open rooftop that you can mount, or a ground area where you can put in a ground mounted array. Also good southern exposure, so we tend to try and want to orient the solar PV system more or less directly south, so you want to have good exposure to the south, and also shade-free location, because the less shade, the more solar production that we get. So in system sizing, one of the big limiting factors is the available space that you have. So a certain roof can only support a certain amount of solar PV panels on the top of it. Also, a ground-mounted array has only a certain amount of open space. You also want to pay attention to your annual electric usage, because a lot of the times we want to try and size a system for a certain percentage of your electrical use. And then also budget. What is your budget with these projects? If you don't have a higher budget, that doesn't mean you can't install solar PV. We just would need to reduce the size of it. And then also the electric utility policy. And this varies across different utilities in different states across the U.S. And the big thing that we want to look at is the net metering policy, which basically is the way that the utility basically offsets your electric usage based upon your production. And so some utilities will provide you a payback or offset of your direct utility cost per kWh, and some have a little bit different policies which offer offset at maybe their own cost of purchasing that wholesale electric. So advantages of solar PV is you have an indefinitely renewable resource. The sun's always going to shine, and if it's not shining, we're not going to be here anyway. So it's a great resource in that sense. They're low maintenance, so solar PV systems have few moving parts compared to the other renewable energies that we're going to be talking about here today. They have a proven track record. There are systems that are 30-plus years old that are still producing at a lower percentage, but they're still producing power for their owners. And they're generally safe, so the PV panels, they're safe in the sense that, once again, with less moving parts, you have less issues, and also installation's a little bit easier due to the module aspect of solar PV systems. Some of the few disadvantages of solar PV is the production is not constant, so that's basically when the sun's not shining, you're not getting production. And they are still a little bit of an initial high investment cost in terms of getting them installed. So. A little bit of, there we go, okay. So some case studies that I just want to cover quickly to give you an idea of some different installations. This one's for a dairy. It consists of the installation of 333 solar modules that are, the production's estimated to cover about 32% of the farm's electricity use. The initial install cost is around $216,000, but this one would receive a 55% payback from a REAP grant and federal tax break. And then the first year electric savings from the system is roughly around $10,386, with the system payback of 11.2 years. One of the things that I would like to emphasize when doing with solar PV is the modular ability of solar PV. So the systems can be scaled up and scaled down to size based upon your budget and your site restrictions. So it's a great renewable technology in that sense. And so this one is for irrigation. As you can see, the little tiny red outlined area is the proposed location for this array. It would consist of roughly 96 solar modules that are estimated to cover about 35% of the electrical use. Now, this system is located near a pumping station that feeds an irrigation overhead irrigation system for a cash crop farm in Colorado. The initial install cost is roughly $73,000, but similar like the last one, they'd receive about 55% back in the form of a REAP grant and then federal tax breaks as well. First year electrical savings is roughly around $5,200, and this system has a payback of 6.4 years. Now, I'd like to kind of stress the difference between the dairy system, the dairy case study here, and the irrigation is it really is in the differences in the utility rate structure. And so they have a similar install cost as $1 per watt install cost, but the utility rate structure is more favorable in the irrigation project. This one with the irrigation project has a higher offset for their electrical cost for what they produce on their PV system. Now, with these systems, we're generally shooting for about 35% of production. And now, where this comes into play is relating back to the utilities policy on this, and so. Really, we're shooting for that 35 in order to maintain a good offset cost. Also, a lot of utility companies have certain size restrictions on solar PV, which make shooting for a little bit smaller percentage can make the permitting and the application process move quicker as well. And so now I'll jump on to the solar thermal systems. And so basically, a basic quick explanation of a system. It can be seen in a car. This is of Mark's. He doesn't have any more, but it's his old Toyota Corolla. And when you walk out into a parking lot, let's say you go to the grocery store and it's a hot summer day, you get back into your car a lot of times. But when you get back in, you have to roll down the windows or crank the AC because it's really hot inside. And so basically, with solar thermal, we're using the sun's rays to directly heat a source, and those different types of sources can be. Let's pop ahead to this one. The different types of sources can be the energy storage can be of air, which would be the case in Mark's car. Also, an option is storing in water, and also there are solar systems that can capture and store that thermal energy in the heat. Just want to pop back quick here to this previous slide. Yeah, we can pop back quick to that previous slide. No, maybe not. Okay, there you go. So similar to solar PV, what we're really looking at for these systems are, once again, your location and your solar resource. And so, like in PV, places like Colorado, Arizona, and New Mexico have a higher solar resource. They have a higher possibility of generation based upon those locations. And so there's multiple different system options that we're looking for. Like I mentioned, there's the different energy storage options, but then also the important thing with solar thermal system is really designing the system based upon your needed temperature. And so we have multiple different types of temperatures with the low, medium, and high systems. And so I'm just going to jump into talking about those different systems. So a low temperature system is a system where it's less than 100 degrees Fahrenheit, and lots of different, some farms actually have these systems in place already, and this can be seen as in greenhouses, and like Mark had mentioned, in field drying of your crops. So they're leaving them in the field and letting the sun and wind do those drying. Livestock watering, basically in colder climates, trying to keep livestock water from freezing. And also unglazed plastic collectors, which can be as simple as a box that you make with a plastic sheet on the top of it that collects that heat and the sun's energy and heats air that can be pumped into an area. Also, a lower temperature requirement would be an aquaculture system as well, which is an aquaculture. If you're not familiar with aquaculture, it is the growing of fish or plant species together in one system. And so then covering medium temperature systems with between 100 and 150 degrees Fahrenheit. These systems are the most common systems that are out there that you've probably seen possibly on houses. So the different types of systems can be evacuated tube collectors, which can be seen in the lower left-hand corner. Basically, these are tubes that have the fluid running in them, and they are usually vacuum sealed, which increases the amount of solar gain that is hitting that type of fluid that is being heated. You also have glazed and flat panel collectors, which are an older solar thermal technology, and those can be seen in the middle folder, which basically involve a box that is sealed up and has a flat plate collector on it, which commonly is used copper piping, in which the fluid is run through the copper piping and that heat is exchanged to that fluid. Then also a little less common option out there is the concentrating solar collectors that can be seen in the right-hand area where basically you are collecting the solar resource from a wide area and directing it onto a smaller area, which tends to have that fluid that we're trying to heat run through there to heat it. And then also these higher temperature systems of over 150 degrees, these are going to be less common for agricultural systems. A lot of times these are most commonly used in utility scale. And one thing I'd like to also say that mention is across these different systems, low temperature to high temperature, is it usually as the lower temperature tends to be lower cost, medium is a little bit more cost, than the lower, and then the high temperature is the highest cost type of system, generally speaking. And so basically similar to the medium temperature concentrating solar, it's a similar technology where you're gathering the sun's solar gain over a larger area, directing it towards a smaller area. In this photo, the panels that you see are directing that sun's energy into that little tube that's running the length of those panels, which has the type of fluid running through it, whether it's water or more commonly a glycol solution, and that directs the heat towards that solution that is then heated. Some energy storage examples, like I mentioned, we have air, water, and different soil. The photo to the right is actually of a business in Milwaukee called Growing Power, and they use solar thermal panels that are located above a walkway to heat water that is used in their aquaculture system, which grows different fish and also lettuces and greens. Now their system is a hybrid system too, where it has a backup boiler. And in these certain systems, such as aquaculture, you want to make sure you have a fail-safe. So when, let's say you have a cloudy day, you have a backup to produce that water heat that you needed, because you need that temperature and that water to remain at a constant level. Other options are solar as the air. That kind of the easiest example of that is the greenhouse, where we're collecting that energy in that greenhouse and heating that air. Another option is soil as well. So similar, some systems will capture the heat from the sun and then trap it and store it within soil directly, or some systems are made out of rock deposits as well, in order to store that energy, which is then later pulled out of the soil and used for your application. And really what we're trying to do here, similar to solar PV, is we're really trying to match the energy produced to the consumption. We're talking about lower high technology, so we're looking at seasonal or annual needs. So do you have a high heating need throughout the year, or is it a seasonal application, and that will affect the type of system that is the best for your agribusiness? And the big thing is the critical temperature point, or variable temperatures that are acceptable. And also low and medium or high temperatures is something that we're looking at, like mentioned before. So really the big thing with solar thermal is, what is your temperature need? Do you need a lower temperature or medium or higher temperature? That's really going to affect the system that works best for you. Now the payback on solar thermal systems is, we have a figure in here roughly of 20 to 500 years without incentives. We have I've worked on projects which have 200-year paybacks, and that's not the greatest payback. But in agribusiness systems, you can get those costs down to 10 years or less is a possibility. And really, a big component of that is matching your system to your heating needs. Now, if you need a low temperature or medium or high, like you're saying, if you only need a low temperature but you install a high temperature system, it's the wrong application. High temperature systems are more costly, so you're going to have a longer payback. I'll pass it off to Mark here.
Thanks, Drew. So now we're going to move into some technologies that take a little more work than the solar ones. And starting out with geothermal, just to, there's a couple different definitions of geothermal out there. One is the geothermal energy, which is typically the places you hear about it in Nevada, where they're able to produce power based on the energy of the ground out there. The map on the left is the temperature of the ground 10 kilometers below the surface. Translate that into miles, that's about 6 miles down underground. Those are not systems that you're going to put on just a standard farm. If the ground temperature is that hot, closer to the surface, you're generally not going to be farming there. So what we're really talking about is geothermal is a heat exchange between the ground, and really what it's doing is it's using the ground as a battery for heat storage and the ability to pull heat and putting a heat pump on it. So the official term for that is a ground source heat pump. And what it does is you'll have essentially, it's similar to a compressor, but it's designed a little bit differently. You see a picture on the upper right-hand side. The heat pump will pull heat out of something that needs to be cooled, can then transfer that to either to the ground, or if there's an immediate need, immediately over to an immediate need for heat. And really all it does is it uses electrical energy to exchange heat in different places. So what you need to do over the course of a year is have a balance between your cooling need and your heating need. And so long as you have that, you can use the ground to even that out if you have cooling in summer and heating in winter. Relating that back to our some of our typical agricultural operations, poultry and hog are primarily heating applications. There's minimal cooling. Most of it's done through ventilation, so ultimately those are not a good match. The ones on the bottom, the greenhouse and vegetable storage, depending on the type of operation, for the most part, you're either you either have a lot of heating or you have minimal of either. Most of the cooling is again done through ventilation. There's not a lot of active cooling on there. The one left is dairy, where there is a large cooling load of the cooling the milk. You have a hot water need for sanitary, for cleaning out the pipes, and then also some. Generally, there's some miscellaneous buildings and the milking parlor that needs space heat. On the right is an example of a dairy farm. The top section of bullet points is a heat pump size to meet the sanitary need. So it eliminates the ground loop, and you put in a heat pump to transfer the fluid or transfer the heat out of the milk into your hot water. Project cost of somewhere in the range of $80,000 for a pretty substantial sized dairy farm, and payback depending on utility rates and how well it can operate in the 3 to 8 year range. Now, if you take that and you size it up for all the heating needs, include the space heating and the ground storage loops for that heat, your project cost balloons up to $400,000, more than 4 times the cost, just by constructing that ground loop. You get to utilize more of the heat that's coming out of that milk, but the and payback doubles from the 3 to 8 year range to 13 to 17 years. So, some components of a heat pump that are critical in, at least in dairy operations, is a heat pump is not going to heat water above 130 degrees, is going to be kind of the max temperature. So you're still going to need one of those hybrid systems where there's a boiler after your water collection. You're going to be swapping what you normally use to heat water with electricity. And so there's going to be a little bit more electricity in the cooling of the milk, and that's going to be offset by the heating you don't have to do. So you're swapping fuels you use on the farm. Some of the biggest questions, this is not a typical application in a dairy around in the U.S. There's just a couple installs in the U.S. There's in other countries, I've been told there's more, but my travels haven't taken me there yet, so I can't confirm that with my own eyes. So a few of the really big questions on a ground source heat pump for ag operations is who's going to provide the service, the maintenance of the system, who's going to design it, who can sell the components to you. Everything's out there. They're generally, I've had best luck in talking to the industry. You talk to the industrial heat pump suppliers, and they are the ones that can generally best figure out an agricultural process because it resembles industrial systems. Moving into wind power. This is, again, the wind it blows to spin a turbine. An important distinction from the water pumping turbines of black and white pictures that were circulated when this new type of wind turbine electricity started. The turbine is actually spinning a generator inside, and in order for a generator to create electricity, it needs speed. It needs a speed much faster than the wind will push something. So think about your car engine; it idles at 1,000 RPM. You can never push something around that fast. So the blades you see with those three blades are actually more like airplane wings. They're being kind of lifted around in the circle from the wind, and the speed is going to be a multiplier of the wind speed pushing it. But ultimately, you're reliant upon that wind blowing and creating the speed you need to create electricity. So then, out of the electricity generator that's up on top of that pole, the electricity will come down, go through an inverter just like a solar system will, and then connect to the electric grid. And ultimately, the wind blowing is more variable than the sun shining. So you need to make sure that you set up an agreement with your utility if you're going to go forward into a wind, and make sure everybody is okay with that agreement moving forward, because there's been a lot of strange things that happen when the wind blows things. Another fun topic in wind power is working in Wisconsin here in wind power. I travel around the state, do assessments for people and what their opportunities are, and been over to Iowa to do it. And if you're not familiar, the Wisconsin-Iowa border, down in the southwest corner of Wisconsin, Iowa connects in. I did the best I could to match these maps up so you could still see it. But essentially, the Wisconsin wind is yellow, brown colored in there, kind of on the lower end. And that's considered some pretty good wind in Wisconsin. You're feeling all right. You can put in a wind turbine there. You cross the border to Iowa, you get that same brown color, and they think their wind is barely anything. Nothing's blowing, because they have the western side of Iowa that over there with some of the best wind in the country. So there's a little bit of a perception on how windy it is at your site that ultimately I think a lot of times plays turns people off to wind power before they've even looked at it and get a chance. Another perception issue is how big are the turbines. This is a little bit of an old slide, but the wind turbines on the right are utility scale. The utility scale are actually larger than that now. They're up to 3 megawatts, sometimes more than that. The ones that you're going to be putting on your site are the ones on the left side, the 3 little ones over there. And those are manageable on electric grids that connect to agricultural facilities. So, ultimately, your collector for the wind power is how big of an area your blades cover. So you can see how much the utility scale collects as opposed to your individual site. So the 2 maps on this page are the difference between a 30-meter height and an 80-meter height, so about 100 feet high and about 250 feet, 300 feet high. You can essentially, the farther you move away from the surface of the Earth, the faster the wind blows, the more even it is, and the easier it is to get wind power out of it. Again, why utility power works in some places where individual smaller sites do not. So the wind power advantages are, ultimately, once you get it up there and build it, it's free energy. It has the opportunity, as it gets larger, to produce more energy than solar PV. And ultimately, since it's on a post, it takes up a lot less space than solar PV. As you start to get larger, as you start to pass 50 kilowatt systems to 100 kilowatt systems, ultimately, I got to worry about cost. I like the little graphic on the right side. Those are utility scale people, but generally, you may want to do your homework on the folks that, if either of them look like that coming up, offering you the best deal in the world, you may want to check into them. So, right, wind powers, they can be very expensive to install, but actually the biggest cost, ongoing cost, is the operation and maintenance of it. Ultimately, you have a generator up on top of a post that's spinning around in the wind. Anybody who works with a tractor would, I'm sure, love to tell you how much maintenance their tractor would need if it was on top of a post spinning in circles. So, and one comment about the noise of a turbine. Turbines they do produce a noise. It's a very low sound. It's not a typical sound that you'll hear anyplace else in your environment. So if you measure it in decibels, it comes out pretty low. I mean, people compare it to whispers or a meowing cat or something, but it's a new sound in the environment, and when it first goes in and first starts spinning, you'll hear it, and it'll drive everybody nuts for a while. And then, just as if you got a new refrigerator in your kitchen, the sound of it will drive you nuts for a while, and hopefully it becomes part of the background, part of your environment, and that sound just melds into the background. All right, now I'm going to touch quickly on biomass, biogas, and then hydroelectric moving forward here. So, ultimately, the base definition of biomass is it's a burning material that was once living to produce heat and energy. That ultimately the burning process releases greenhouse gases and some of the other components and gases that are being regulated more and more. But ultimately, when you're using biomass, you take a step back, you draw the picture a little bit bigger, that if you're using biomass, you're going to have to replant. And over the course of the next year, your replanting is going to suck up the emission releases from the burning, and ultimately create a cycle which is pretty close to neutral for wood, waste, grasses, grains, oils from vegetables, household garbage, but a lot of people have kind of pull out in recyclables or kind of individual streams of garbage. So the biggest criteria is you're going to have to acquire your fuel, whether that's going out on your own property and chopping down the trees, or you're purchasing pellets from your local co-op. You're going to need to store that on site, handle it, get it over to your boiler. Once it's in there and burning, there's temperature and environmental controls you're going to have to control. And then out the back end, there is an ash, which is, depending on, again, what you're burning, is a fertilizer, can go back on the ground. The biogas system is similar, that it deals with organic material, but it doesn't burn it. It ultimately has the most value in agricultural facilities as a management tool for manure. The biogas is produced as the manure decomposes in an anaerobic atmosphere. That's an atmosphere without oxygen. And it produces methane out of there. So the kind of 5 components of the system, again, similar to biomass, is you need a collection system for your manure. You're going to need the digester. You're going to need a gas collection system, a way to utilize that gas coming out, and then ultimately a waste handling. The solids will add up in the digester and will need to come out. So the fuel can most times in agricultural facilities is manure coming from dairy, swine, or poultry. There are places around the country that collect food waste or organics from nearby cities or towns or restaurants to add in there. Through the digestion, the system produces methane and also sulfides, hydrogen sulfide. It has a bunch of different names, but ultimately, if you hear something with sulfide in it, what it is it's a component of the biogas that comes out that, when mixed with water, creates a corrosive acid. And if you don't clean it out of there before it gets to your engine generator or any place you're going to use the gas, it'll corrode away your metals over time. So that's in your handling, you got to clean the gas. You also need to be able to pull the solids out of there and handle those and get those back out on the farm. The solids are going to be much less handling coming out of a digester than would be if you're handling the raw manure. So most likely that component's already in place. And then once you have your gas cleaned, you can go to a boiler with the biogas. You can go to an engine generator to create electricity. You can even clean and pressurize the gas to a point to be able to put it into a natural gas pipeline and create a sale arrangement with the pipeline owner. Just real quick, a lot of the benefits to a biogas system, especially currently because they're offsetting natural gas, does not have a ton of value right now, is in the environmental side, the odor management, water quality, and well, who knows if greenhouse gases are going to get counted or not, or when. So, so I just put down biogas systems ultimately are large systems. They don't scale very well to smaller systems. A lot of people are working on systems that'll make a smaller one work and be cost effective. To date, I haven't come across any that have kind of broken the magic cost barrier to make it work. As far as producers' time, the agricultural time, this is a job that needs to get added to the list of jobs that are done by folks on site. You're going to need to manage the system, both the manure handling, the operation of the digester, and the environmental controls, the gas cleaning. Like these all take time, and will get out of alignment if you let them go too long and don't keep them up. Water availability is critical here. If you have a dry manure coming in and not a lot of water sources, you're not going to be able to find enough water to create the anaerobic environment necessary to create the digestion. And then again, what can you sell the gas for? Are you better to turn it into electricity? Does the bedding have any value? Are going to be the critical components. Hydroelectric is another age-old technology that's being refined over time to be more and more useful on individual sites. What you need is water at a higher elevation and a constant flow to be able to come down, and you can siphon some of it off, run it through a turbine. It works the same as very similar to a wind turbine in that you're going to run it through a pipe. Ultimately, your collection area is how much water is coming, or your power is how much water is coming through there and from how high, and it's going to push the turbine around in a circle. The water has a little more density than air, so the turbine works a little bit differently, and it can actually push as opposed to needing to fly like a wind turbine blade. So, if you have a site that works for hydroelectric, once they're operating and tuned in, they go pretty good without. With the kind of just the minimal amount of cleaning, and there are not a lot of moving and rubbing parts aside from that turbine, making sure that the blades stay good in there. There's a scale component to hydroelectric, so the costs are generally high if you have a low flow coming down in your pond or in your stream. So you're gonna want to kind of aim for the biggest size you can get in order to make it worthwhile.
All right, so just to kind of go over, wrap it up here, what Mark and I have covered, I think one of the big things to take away from different types of renewable energy that we've discussed is basically the complexity of the systems, and then also the maintenance of those systems. And so where you have something like solar PV, which is pretty straightforward, pretty easy installation, there are not a whole lot of moving parts, so operations and maintenance costs are going to be lower. Whereas when you start moving up into solar thermal, wind and geothermal and hydro, you're really starting to add complexity to the systems, more moving parts. which would lead to more operations and maintenance and more management. And then also, looking when you then scaling it up to the biomass or biogas system, the complexity increases. So you're more moving parts like geothermal and wind, but now you have even more management of maintaining fuel source and the components within the system as well. But with just the solar PV, it's really going to be the easiest that you're going to be installing out of all the systems. Solar thermal, once again, we're really trying to match that heat load, that temperature to your application. And like Mark mentioned with geothermal, making sure that you have that heating and cooling balance, so you have a heating need during the cooler season and a cooling need during the warmer season. And then with wind, what is your wind speed availability? And are you going to commit to paying someone, or are you going to learn how to climb up on top of that pole and work on that generator and wind turbine? Really, with biomass and biogas, the big question is the size and the production of that fuel source, and is that additional work that comes that is the management involved and of that system, is that really worth the offset value of the cost of the system? And thank you for tuning in. And if you have any questions that you'd like to ask Mark or I, if you would type those into the comment, the question box, we'll be able to see them displayed, and we can answer those questions for you.
All right, I do have a question coming in here. Was the payback on photovoltaic a national average?
No, that payback was specific to that individual project in that case study, and it really varies utility by utility, and I don't know what a national average would be, because each state has its own regulations that a utility needs to follow, and then each utility has its own rate tariffs and on what that value of the electrical kWh is and the kW reduction potential.
Yeah, and in those instances, you'll run into occurrences where the utility will offset the cost of the cost per kilowatt hour that you are charging you, or we've seen some that will provide that payback as less than half of what they're charging per kWh as well.
All right. We've got one more question here. Can you further discuss the factors that allow a biogas project to be feasible?
Yeah. So ultimately, a biogas installation is going to be over $1 million installed. And if you're going to add an electric generator on top of that, you may be close to adding another $1 million to that. So that's going to be driving your. I guess that's your cost to claim your opportunity of that your manure holds. So the simplified ones is we don't begin to look at it until at least there's 500 head in the dairy, 2,000 pigs, and that there's a location where manure is currently collected and it's relatively clean. So the and you know, in the case of pigs or poultry, that you know the farm is operating year round and not taking a few months off because the digester keeps working and needs to keep being fed, or the ecosystem inside dies. So just you're looking at it, these are the traditional place where a digester works is a pretty intensive production agricultural animal facility, and then you know once you have that as the base, you can start looking at additional components to start bringing in, or you know whether you need to add water to your manure, or whether you can bring in some organics to pump up the gas production.
All right, we've got a couple more questions, but we are running out of time. The people who have put in their questions, thank you so much, and we will answer them via email as soon as possible. But again, thank you for spending your morning with us. And if you do have a need for the recording, go ahead and just email me. And I hope you guys have a great day. Thank you so much for joining us today.